Hello everyone, thank you for coming. My name is Ricard Durall and today I'm going to present generative models for transfer learning on seismic data. I did this work together with Valentin Tschannen, Norman Edrich and Janis Keuper. Imagine that we could automatically interpret the seismic data. This would be excellent news because we could get rid of picking manually the data, which is a tedious and very time-consuming task. In fact, we don't need to imagine it anymore since it's already happening. Thanks to the recent outstanding progresses in deep learning domain, nowadays it's possible to automate some tasks that before were exclusively done by human experts. Just to give you an example, here on the slide you can see an illustration from Where is Wally's book. The goal in this book, as you probably know, is to spot Wally as fast as possible. This is usually a quite challenging task since they are very crowded pictures full of distractions. Using deep learning approaches allow us to find Wally in a blink of an eye. In this case, I'm not going to make a spoiler so that you can later try to find him. I just show you one toy example with Wally, but this can be extended to real-world applications. Here we have a short summary which contains a few examples in the seismic domain, like faults, solid bodies, horizons, and diffractions. Although they are completely different tasks, they have in common that often we need people with expertise on the field to look for these events on the data. That's why the community keeps on developing tools to assist these experts. So our case of study focuses on both diffractions and faults. Here in this slide we can find the main characteristics of them. On the one hand, we have diffractions from shallow offshores, where the scattering events come from hard boulders beneath the sea surface. A real case scenario for this data could be to know where the boulders are located and where the boulders are located to take them into account when drilling. Or a second scenario could be, for instance, for the interpretation of karstic carbonate reservoirs. On the other hand, we got the faults. In this case, the main characteristics are that they are clean and regular in the deeper parts of the data, but subtle and irregular in the central regions. Okay, so we have seen our case of study. Let's now have a quick look at some deep learning traditional approaches that try to deal with it. Option A, on the left side, shows a simplified pipeline where we use real data with labels to train a semantic segmentation model. Given that we have enough data, this model would be the best choice. However, labeled data or annotated data is very expensive, and usually there is a shortage of it. The red cross indicates this problem. Option B, on the right side, does not have this problem. The reason for that is because this model uses synthetic data. Therefore, it is possible to generate large amounts of data of labeled data at barely no cost. Nevertheless, this method also has a big flaw. Since it is learning from synthetic data, its performance with real data at testing time could be considerably worse, making the model eventually quite weak. And this is what the second red indicates in this model. Just to recap the last slide, we have a problem or a challenge, if you want, with this data. Either we don't have labels or we don't have enough labels, or the synthetic data is not good enough. Here we present two possible solutions. First, we can try to generate more realistic synthetic data, and therefore we can try to avoid the gap in performances between training and testing. Or a second option could be to implement some kind of domain adaptation technique that will allow us to use other training data for the given problem. In this talk, however, we are gonna focus on the first solution, generation of synthetic data. In particular, our approach or solution is an end-to-end system that exploits a generative model to improve the main task, which is the semantic segmentation. So then our first ingredient is the generative model. The goal of it is to try to approximate the real data distribution as much as possible. For instance, here on the slide, we have two Gaussians, okay? One that represents our generative model distribution, which is the blue one, and one that represents the real data distribution, which is the green one. We can imagine that when we start training our generative model, its distribution doesn't match with the real one, and this is what we see here on the left side. And as a result, if we take samples from our model, we will get monster dogs in this case. So basically, we're not going to be able to produce realistic images because the distributions don't match. Hopefully, by the end of the training, our model will match the real distribution much better, and we are going to be able to produce realistic dogs when we sample from it. So we could say that intuitively what we want is that the probability distribution from our model is equal or as close as possible to the real one. Now that we know what a generative model does, let's look how it fits in our model. The main idea is pretty simple. We basically take option B, the one that works with synthetic labels, and we add on top of it a generative model. In this way, the generative model will add a second source of label data, which will boost the segmentation results. In this work, I haven't mentioned it yet, but we are going to use the Generative Neural Networks, or GANs for short, as a generative model. This approach works as follows. We have two networks, one called generator and one called discriminator, and the idea is to train them using a minimax formulation where the objective function basically forces the generator to learn to produce realistic images that can cheat the discriminator. So here on the slide you can see how the generator takes from random noise some samples and then tries to produce an image, and then this image goes to the discriminator, and then this discriminator needs to decide whether this image is real or fake. And by doing this in a kind of iterate way, they're gonna improve both of them, and eventually the generator is gonna be able to produce images that are as similar, that they are really close to the real ones. A variation of this approach, it is called the Cycle GAN that is depicted below. This well-known model has the capacity of generating images according to a certain domain. In other words, instead of taking random noise as input and then generating images as vanilla GAN does, this model takes an image from domain B as an input, for example, and generates a new image in another domain, in this case domain A, as an output. And finally, the discriminator does the same job as before, just tries to distinguish between images that has been generated and images that are real. Now we can put everything together, all the pieces into one picture. Here we can see the overview of our approach. Notice that we use both annotated synthetic data and real one, which remember that this real one does not have label information. We can observe how we incorporate the Cycle GAN into our system. In particular, we use it to add a second input in the segmentation network, and in this way the segmentator will be trained on synthetic data and on generated, which is closer to the real one. And by combining these two types of data at training time, we're going to get better results at testing. Okay, so now let's check out the experimental results. But first of all, we need to define the experimental setups. We have trained two individual models, one for diffractions and one for folds. In both cases, we have a dataset for real without labels, a dataset of real images without labels, and a synthetic dataset with labels. Here we can see a couple of examples from each set. Notice that usually real images contain more high frequency components, and it is something that pure synthetic data usually lacks. And hopefully by using this generative model, we're going to be able to capture some of these frequencies that were missed. In this slide, we show the results from our generative model on the diffraction setup. We can see how our system can produce synthetic seismic images in the deep angle migration domain, where the diffraction curves produce the expected patterns. From left to right, we got the stacked synthetic samples, the stack transformation, and the pre-stack transformation. And we can see how the results are pretty coherent, maintaining the main structures. And here we have the results on the detection of diffractions. We have a first figure, top left, corresponding to the real image, so the input. Then a bit to the right, the prediction of our system, and just below the pre-stack. In order to assess the results, we need to manually verify the findings, which most of the time match with diffraction. So these are good news. But the problem here is that every match, well, in order to determine if there is a match or not, we need to check it still by hand. So it's still time-consuming task. Now here we look at the faults. In this slide, we show the results from our generative model. We observe how our system produces more realistic results in comparison with the synthetic data, while keeping the same label information. And this is what is shown. First and third columns are the synthetic data, and the second and fourth are their transformation. And again, here we have the results on the peaking faults. We have a figure on the left corresponding to our approach, and on the right we have the ablation study, where we basically have removed the generation part, so only this option bay that we were talking all the time. Visually, we can confirm that there is a clear improvement when we use the generative model in top of the option B, since we are able to detect more faults, and this is what we see in this slide. And last but not least, some conclusions. In this work, we propose an end-to-end model that allows to both transfer synthetic patterns into real data and to automate the identification of seismic events such as diffractions and faults. We have also seen how combining synthetic data and its realistic transformation seems to lead to better results, and outperforming in this way the traditional methods based on pure synthetic data. Thank you very much. If you have any question, don't hesitate to contact me. Bye-bye.